Hello, everyone. Today we're going to go over section 2.1 on discrete probability. Probability is a way to measure how likely it is for some situation to occur. In order to discuss probability, we will use a lot of terminology that may already be familiar to you. Because we give these terms very precise meaning in mathematics, we need to start by going through some of the more common ideas. An experiment is any activity that produces a measurable result, called the outcome of the experiment. When we say measurable here, we mean any way to differentiate one outcome from another. For example, rolling a six-sided die has six possible outcomes: a 1, a 2, a 3, a 4, a 5, or a 6. The sample space of an experiment is the set of all possible outcomes for the experiment. For example, the sample space for the experiment of rolling a six-sided dice is the set S, containing 1, 2, 3, 4, 5, 6. I'm showing it as the picture of the dice there, but to make writing easier, it is convenient to denote the set simply as the set S with the numbers 1, 2, 3, 4, 5, 6. Many of the exercises that we will work through in this unit will be built around a few simple experiments. Take advantage of this and use props to model the situation to get a better understanding of the situation described in the exercise. Rolling one or more dice is a common choice. In addition to six-sided dice, we may look at dice with 4, 8, 12, or 20 sides. These behave exactly as you would expect. For example, the sample space for rolling a 12-sided die is the set S containing 1 through 12. Another common experiment that we will see is flipping a coin. The possible outcomes are heads or tails, and we write the sample space as the set S containing H and T for heads and tails. Rounding out the list, you will also encounter the experiment of shuffling a standard deck of playing cards and drawing one card from the top of the deck. This experiment has 52 possible outcomes: the ace of spades, the queen of hearts, the two of diamonds, and so on. The cards in a standard deck are each assigned one suit: hearts, diamonds, spades, or clubs, and a value: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king. We usually care about the count of possible outcomes in a sample space. Mathematically, this is the cardinality of the set that forms the sample space. So we will use the same notation that we introduced in section 1.3. We denote the count of the experiment as n of S. That's the count of the experiment with sample space S, n of S. In the simplest cases, we can determine the number of possible outcomes just by creating an organized list of all possibilities. So in example 1, we're asked, how many possible outcomes are there when flipping two fair coins? Assume that the two coins are easy to differentiate. Let's do our 4-step problem-solving process. Step 1, understand the problem. We must first recognize two facts about this experiment. First, each coin has two possible outcomes, heads or tails. Second, the two coins do not affect each other. The outcome of the first coin will have no bearing on the outcome of the second coin. Step 2, devise a plan. We can list out all of the possible results of the experiment and then count them. Step 3, carry out the plan. The first coin could come up as either heads or tails. When the first coin comes up heads, the second coin could come up either heads or tails, so HH or HT. Likewise, when the first coin comes up tails, the second coin could come up as either heads or tails. so TH or TT. Together, that gives us the sample space for this experiment as the set S containing HH, HT, TH, and TT. Step 4, look back at your result. As listed above, this experiment has 4 possible outcomes. Let's talk about event spaces. An event is some collection of possible outcomes for an experiment. Formally, we define an event space as a subset of the sample space of an experiment. From this definition, the event is any one of the outcomes in the event space occurring. For example, returning to our deck of cards experiment, we can define the event of drawing a club. The event space would be the set containing each of the 13 club cards in the deck. So the set E would be the ace of clubs, the 2 of clubs, the 3 of clubs, the 4 of clubs, the 5 of clubs, the 6 of clubs, the 7 of clubs, the 8 of clubs, the 9 of clubs, the 10 of clubs, the jack of clubs, the queen of clubs, and the king of clubs. So the sample space S would be all 52 cards. The event space E is just the 13 club cards. Just as with sample spaces, finding the count of outcomes in the event space, N of E, will prove important later. In our example of the event of drawing a club card, we can count that N of E is 13. In other words, the cardinality of the set E, the number of things inside of set E, is 13. With this background, we can now define the probability of an event as the ratio of the number of ways that the event can occur to the total possible outcomes for the experiment. Symbolically, we write this as P of E, the probability of event E, is equal to N of E over N of S, the number of things in set E, the event space, over the number of things in set S, the sample space. So N of E is the number of possible ways the event can occur. N of S is the total possible outcomes in the sample space. Let's look at another example, example 2. What is the probability of rolling a 5 or higher on a 6-sided die? So our 4-step problem-solving process. Step 1, understand the problem. We're looking at the experiment of rolling a 6-sided die. The event that we care about is rolling a 5 or higher, and we're asked to calculate the probability of this event. We would use our probability formula, P of E equals N of E over N of S. Step 2, devise a plan. Since our formula says to find the P of E, the probability of the event, and our formula tells us that we need N of E and N of S, the number of things in the event space and the number of things in the sample space, this experiment is simple enough that we can find those two values by listing all possibilities. Step 3, carry out the plan. We list the sample space of this experiment, which would be all the different possibilities. When we roll that 6-sided die, the sample space would be 1, 2, 3, 4, 5, 6, because we can roll a 1, we can roll a 2, we can roll a 3, we can roll a 4, we can roll a 5, and we can roll a 6. The event of rolling a 5 or higher can then be denoted as the set E, which would just be 5 and 6. A 5 or higher can only be a 5 or a 6 on a 6-sided die. These would be all of these successful event outcomes. Counting the outcomes in each of these sets, N of S is 6 and N of E is 2. With that, the probability of the event, n of e over n of s, would be 2 over 6. Reducing the fraction, the probability of rolling a 5 or higher would be 1/3. Now let's talk about odds for and against. In many real-world situations, the chance of an event occurring is given as the odds rather than the probability. Before we can talk about odds, we need to revisit another idea from section 1.3, the set complement. The complement of an event, which we denote as E star, is the event that E does not occur. Going back to our experiment of rolling a 6-sided die, consider the event of rolling a 5 or higher. As we saw, we would write this event as E is the set 5, 6. The complement of the event is not rolling a 5 or higher. More simply, we can call it rolling a 4 or lower and write it as E star equals the set 1, 2, 3, 4. Remember, the complement is everything in the universal set that isn't in the set we're looking at. So since the universal set here was 1 through 6, and set E was 5 and 6, E star would be everything else, 1 through 4. So let's define odds. The odds for an event is defined as the ratio odds for equals n of E over n of E star, where n of E is the cardinality of set E, the number of ways that E can occur, and n of E star is the cardinality of the complement of event E, the number of ways that something other than E can occur. So the number of things in the event space over the number of things in the complement of the event space. The odds against would be the reciprocal of that ratio. The odds against is the ratio n of E star over n of E. So like I said, these two ratios are reciprocals of each other. One is just the other one flipped, so you want to make sure you know which one is which. It will be important to remember that either an event or its complement must occur every time the experiment is performed. Mathematically, we can state this as n of E plus n of E star equals n of S. In other words, the event space, the number of things in the event space, plus the number of things in the complement of the event space needs to add up to the number of things in the sample space. The sample space is the universal set for E and E star. Or in terms of probability, we can find the total number of possible outcomes for an experiment by adding together the number of ways that one event can occur and the number of ways that the event can fail to occur. This makes it straightforward to convert between the probability and the odds of an event as long as they are given as fractions. Example 3. The 2018 Triple Crown winner Justify was given 4 to 5 odds against winning the Belmont Stakes in the morning line. The second place finisher in the 2018 Belmont Space, Gronkowski, was given 12 to 1 odds against winning. Assuming, poorly, that the morning line is based only on the horse's chance of winning, what was the probability that Gronkowski would win the Belmont Stakes? Let's rely on our 4-step problem-solving process. Step 1, understand the problem. We know that the odds against were 12 to 1. We want to know the probability. Step 2, devise a plan. Matching what we know to the formulas for odds against and the number of things in the sample space being the number of things in the event space plus the number of things in the complement of the event space, we should be able to calculate the probability, because the probability involves the number of things in the event space and the number of things in the sample space. So we're going to use these 3 formulas to figure out what we need to know. Again, odds against would be N of E star over N of E. N of S would be N of E plus N of E star. And P of E equals N of E over N of S. So let's carry out the plan. We were given the odds against as 12 to 1. 12 to 1 is 12 over 1. Odds against is N of E star over N of E. So N of E star is 12, and N of E is 1. This means that N of S, which is N of E plus N of E star, would be 1 plus 12, which would be 13. Plugging what we now know into the probability formula, the probability of the event is N of E over N of S. N of E was 1, N of S was 13. The probability of the event would be 1 in 13, or about 7.7%. That wasn't too bad. Let's look at another example. League experts predict that the Charlestown Chiefs have a 59% of beating the Syracuse Bulldogs in the Federal League's championship game. Assuming, poorly, that betting odds are based on the team's chances of winning, where should the odds for and odds against the Chiefs be set? Our 4-step problem-solving process. Step 1, understand the problem. We're given that the probability is 59%. That would be 59 out of 100. That's just the definition of a percentage. We need to find the odds for and the odds against. So let's devise a plan. Similar to the last one, we're going to match what we know to the formulas. P of E equals N of E over N of S. N of S equals N of E plus N of E star. And once we do that, we should be able to calculate the odds for N of E over N of E star and the odds against N of E star over N of E. So again, we were given that the probability is 59%. That's 59 over 100. Since probability is N of E over N of S, that means N of E is 59 and N of S is 100. Since N of S equals N of E plus N of E star, that means that 100 equals 59 plus N of E star. And a little bit of algebra would give us that N of E star is 41, subtracting 59 from 100. Now we have N of E, we have N of E star. We're able to find the odds for and the odds against. The odds for N of E over N of E star is 59 over 41. The odds against would be the reciprocal of that, N of E star over N of E, 41 over 59. So the betting odds should be set at 59 to 41 for and 41 to 59 against. Let's talk about expected value. Expected value is perhaps the most useful probability concept we will discuss. It has many applications, from insurance policies to making financial decisions. And it's one thing that the casinos and government agencies that run gambling operations and lotteries hope most people never learn about. Consider the casino game roulette. In roulette, a wheel with 38 spaces, 18 red, 18 black, and 2 green, is spun. In one possible bet, the player bets $1 on a single number. If that number is spun on the wheel, they receive $36, their original $1 plus $35. Otherwise, they lose their dollar. On average, how much money should a player expect to win or lose if they play this game repeatedly? Well, suppose you bet $1 on each of the 38 spaces on the wheel for a total of $38 bet. When the winning number is spun, you are paid $36 on that number. While you won on that one number, overall, you've lost $2. On a per space basis, you have won negative $2 over 38. That math works out to negative $0.0526. In other words, on average, you lose 5.26 cents per space you bet on. We call this average gain or loss the expected value of playing roulette. Notice that no one ever loses exactly 5.3 cents. Most people, in fact about 37 out of every 38, lose $1, and very few people, about one person out of every 38, gain $35, the 36 they win minus the $1 they spent to play the game. There's another way to compute expected value without imagining what would happen if we play every possible space. There are 38 possible outcomes when the wheel spins, so the probability of winning is 1 in 38. The complement, the probability of losing, is 37 out of 38. Multiplying each outcome by the corresponding probability, then adding the products, gives us the same expected value we arrived at earlier. So we make this table: outcome, probability, and then a column for outcome times probability. The outcome of $35 has a probability of 1 out of 38. We multiply those together and we get about 0.9211. The outcome of losing $1, negative $1, has a probability of 37 out of 38. If we multiply negative 1 times 37 out of 38, we get about 0.9737, negative. So when we add these two together, the positive 0.9211 and the negative 0.9737, we get our negative 0.0526, that negative 5.26 cents that we saw earlier. So let's define expected value. Expected value is the average gain or loss of an event if the procedure is repeated many times. We can compute the expected value by multiplying each outcome by the probability of that outcome, then adding up the products. Example 5. A 40-year-old man in the US has a 0.242% risk of dying during the next year. An insurance company charges $275 for 1 year of coverage with a life insurance policy that pays a $100,000 death benefit. What is the expected value for the person buying the insurance? Step 1, understand the problem. It costs $275 for $100,000 in coverage. There is a 0.242% chance of this person receiving the covered amount by dying in the next year. And we're asked to find the expected value of this insurance purchase. Step 2, devise a plan. We can set up our table of the possible outcomes and probabilities to organize our computations. Note that with a 0.242% chance of receiving the benefit, we are left with a 100% minus 0.242% or 99.758% chance that this person receives nothing by surviving the year. Also, by paying $275 for the coverage, this person would receive $100,000 minus $275 or $99,725 if they receive the covered amount, and is out the $275 otherwise. So when we build our table, the two outcomes are $99,725 or a loss, negative $275. The probability of getting the $99,725, which do you really want? You're dead in that case. So, you kind of want the other one. The probability of 0.242% as a decimal would be 0.00242. And if we multiply 99,725 times 0.00242, we get 241.3345. If we multiply the negative 275 by its decimal probability of 0.99758, which is 99.758% as a decimal, move the decimal 2 spaces to the left, 0.99758. We get negative 274.3345. When we add these numbers together, the positive and the negative, we end up with negative 33, which means, looking back at our result, on average, a 40-year-old man purchasing this coverage will lose $33. Again, that doesn't mean that every person loses exactly $33. By and large, most people are going to lose $275, 99.758% of them. But the quote-unquote lucky 0.242% will get $99,725. Not surprisingly, the expected value in the last example is negative. After all, the insurance company can only afford to offer policies if they, on average, make money on each policy. They can afford to pay out the occasional benefit because they offer enough policies that those benefit payouts are balanced by the rest of the insured people. For people buying the insurance, there is a negative expected value, but there is a security that comes from insurance that is worth that cost. Okay, go ahead and try the section 2.1 homework. Next time, we're going to go ahead and look over section 2.2.